Okay, so section 5 is on the central limit theorem. It's kind of an important theorem when you're dealing with the kinds of probabilities that we've been discussing here, because it gives you some some parameters in which you can apply the stuff that we've been using when it doesn't necessarily fit the big pattern. So we have normal distributions, standard normal distributions, and we talked about the formulas. But the thing that you should be aware of when we're looking at probabilities, we're looking at the idea of randomly selecting one person for that group. Okay. What if we selected a bigger group? Okay. Now, we know it should give us more valid data in terms of the probability. So how does that extra information affect the formula and the procedures that we're going to work with? Okay. Well, it's not going to affect the formula as much, okay, to answer that question, but it is going to give us a more accurate look at the probability associated with the situation. Okay. So up above there in the directions, the notes up there, it says the central limit theorem tells us that for a population with any distribution, the distribution of the sample means approaches normal as the sample size increases. So the bigger it gets, the more we can generalize the information. Okay, so if the sample size is large enough, the distribution can be approximated by normal, even if the original is not normal. Okay, if the original population isn't normal, we can still treat it as such. And that's what makes this kind of powerful, is that we can tie in some things we know with a situation that doesn't, like I said, doesn't fit the parameters that we discussed earlier. Okay, so the kind of magic number that we use with the central limit theorem is the number 30. So you have a sample size of 30, then there's some things that we can look at. So look at the three conditions that they talk about, three cases. Okay, so number one, for a population with a distribution, if n is greater than 30, then the sample means have a distribution that can be approximated by normal. Okay, now I want you to notice how they've shifted the standard deviation. They took the standard deviation, the mean stayed the same, but the standard deviation is now sigma divided by the square root of n. Sigma is the population standard deviation, and n is that sample size. We're going to take the square root of that. Okay, now, so that's if it's greater than 30. Okay, if it's less than or equal to 30, okay, and the original population is still normal, okay, then the sample means have a normal distribution, and again, we use that same sigma over the square root of n. Okay, so greater than 30, less than or equal to 30, okay, we're going to make that modification. Now, here's where we have to be careful. If the n is less than or equal to 30 and the original population is not normal, then we cannot calculate the probability. Okay, so that's where we've got to be careful, is less than 30 and skewed, okay, skewed, which is not normal, okay, then the central limit theorem does not apply. Okay, so they give some notation. I'm not so concerned about that. Okay, so applying, this is the two kinds of things you're going to see in the problems, or applying the central limit theorem or not. So if we're applying it to an individual value, in other words, we're selecting or working with one individual, we use the z-score just as we did previous. Nothing changes there. It's x minus mu over sigma. But if we are going to work with a group, okay, then we change the z-score to this. x bar minus mu over sigma divided by the square root of n. Okay, that will give us a little bit more accurate z-score, and from that z-score, we get a better picture of the probability. Okay, so a lot of the problems you're going to see right off the bat, they're going to say, find the probability of 1, find the probability for a group of 9. Okay, for example, because they want you to be able to perform the calculations, and they want you to look at those values and compare them. Okay, look at, how far off is it for 1 versus 9. You would think it'd be pretty close, but you're going to find quite a bit of discrepancies. Okay, so but other than that, you're still going to have find the probability at less than, find the probability greater than, find the probability between. The same scenarios that we've been doing throughout this chapter. Okay, so let's look at what they're going to do. Okay, the problems, there are, I guess, 8 problems that I've given you. Okay, but the problems have multiple parts. Okay, so there's not a lot to do, but you'll see right off the bat how this is going to be affected by this formula, and you'll see that in the wordings also. So look at number 3. Okay, 1 and 2 are similar, 3 and 4 are similar. All of them deal with SAT scores. They give you up in the directions that the mean is 1,518, standard deviation is 325. So, number 3 says, if one SAT score is randomly selected, find the probability. Okay, so I give you, so we're doing a between problem. So, we know that it has to be a subtraction problem. So I want to find the probability for part A here. What's the probability that x is less than 1,575 minus the probability x is less than 1,550? Okay, so I'm going to convert both those to z-scores. So 1,575 minus 1,518 divided by 325, and 1,550 minus 1,518 divided by 325 again. So let's calculate those. Okay, so I get 0.18 here. And I'm going to round this up to 0.10 here. Okay, so again, those are z-scores. So the probability that z is less than this minus the probability that z is less than this. I can now go to my table and start looking up values. 0.18 is 5714. 0.10, 5398. Okay, and I'm going to subtract those out. So 0.0316. So I got a 3.2 percent probability of selecting someone between those SAT scores. Okay. Now, I'm on part B now. I'm going to do the same thing. I'm going to start off the same way. X is less than 1575. X is less than 1550. Same numbers. This time N is 25. So I'm going to take 1575 minus 1518 divided by 325 over the square root of 25. Okay. So okay. So subtracting, dividing, again, here's the modification because the group size has increased. I'm going to do the same thing over here. Now remember the square root of 25 is just 5. Okay, so when I divide those things out on the bottom, I'm going to put those in parentheses, and I'll put the top in parentheses as well, just to make sure that it does my order of operations correctly. Okay, so look how much it affected the z-scores, okay, by just plugging that in. So when I did the arithmetic up here for one person, I got a z-score of 0.18. When I did it for 25, I got a z-score of 0.88. When I did it, this value here for one person, I got 0.10. Here I've got 0.49. So we'll see what happens to the z-scores or the percentages when I look them up, but it's already made a big impact on the z-scores. So 0.88, 8106, and 0.49, 6879. Okay, so subtracting those, I get 0.12. Okay, 1227. Now, again, think this is what this is saying, and it should make sense to you here. If I've got a huge distribution of people, okay, and I select one person, okay, okay, I have a 3.2% chance that that one person is between these IQ or SAT scores. Okay. Now, if I select 25 people, okay, I have a 12.3% chance of selecting a person that falls between. So again, that bigger number means you should improve. Your chances of having that happen should improve. Okay, but again, the procedures on less than, greater than, and between have not changed. The only thing we've altered here is that based upon how many, the subgroup of people we're selecting, we have to modify our z-formula, our z-score formula, to accommodate that. Okay, so that's all. The problems are going to vary in terms of different distribution values and such, but other than that, everything else is going to follow true to form. So again, once you get used to this procedure here early from the first couple sections, then you see it's pretty much consistent with everything else we've been doing. Okay. On number 5, there's a couple things I wanted to talk about there. It says in the directions up there, based on data from the National Health and Nutrition Examination Survey, assume that weights of men are normally distributed with a mean of 172 pounds and a standard deviation of 29 pounds. Now, what they're going to ask you to do is they've got basically you got 12 components of problems using that same data. Okay, kind of like they did previous, but it's all grouped into one question. Now, they're going to, it's in broken up here. Okay, do it for one, do it for more than one. Okay, and see what happens. Probably the biggest part of these, if you look at J and L down the bottom, okay, it says, why can the random or central limit theorem be used in part I, even though the sample size does not exceed 30? Remember, that was one of the parameters here. Okay. If you have a sample size on I of just 25, what's key to this is that the original population is normal. Okay, and that's what it says up in the directions. It says assume the weights of men are normally distributed. So why can the central limit be used? Because the distribution is normal. Okay, and the same thing is true for part L. Again, it's because we're working with a population here that is normal. Okay, now let me give you, let's go through, I just want to give you a couple more freebies here. So let's do a greater than one. Part D. If you have 100 men are randomly selected, find the probability that they have a mean weight greater than 180. Find the probability that X is greater than 180. Okay? Well, that's going to be the same as finding the probability of 1 minus X is less than 180. Okay? It's the other side of the line. So, take the 180. Let's find the appropriate z-score. So, 180 minus 172 over 29. Now, notice the X value is always the number that they're giving you to work with. Okay, the mean value, always is subtracted second, standard deviation on the bottom. But this is the X value that's originally given in each problem. So this becomes 8 divided by 29, or 0.26. Okay, 0.28. So 0.28 is my z-score. Okay, now if I look up, so this is the probability of 1 minus the probability of Z is less than 0.28. Let 0.28 is 0.6103. I get 0.3897. Okay. Oh, wait a minute. Sorry, that's going to be the answer to part C. Okay. Okay, because what I forgot to do is I forgot to figure in that this group has 100 men. So let's go ahead and do that's part C. 0.3897. So when I do my Z-score, 180 minus 172 over 29, square root of 100. Okay, just checking my math here again because something doesn't look kosher. Okay, so I get Z-score of 2.76. Okay, yeah, which again, my only check-in because that is hugely different than the Z-score that I was working with for just one person. Okay, so again, I'm going to take 1 minus the probability that Z is less than 2.76. Okay, so when I look that up, 2.76 is 0.9971. And 1 minus that is 0.0029. Okay. So again, and we're selecting a much bigger group. Okay, so the chance of that happening evidently is going to be pretty rare. Okay, within that. So, but just remember, read it carefully. Are you selecting for one? Are you selecting for a group of however many? Okay. On the back side of this one, on number 8, it says engineers must consider the breadths of male heads when designing motorcycle helmets. Okay, men have head breadths that are normally distributed with a mean of 6 inches and a standard deviation of 1. Okay, so this is a less than. So if one male is randomly selected, find the probability it's less than 6.2 inches. And let's see how that comes out. So the probability that X is less than 6.2. So 6.2 minus 6.0 divided by 1. Okay, so we get a z-score of 0.2. So the probability that z is less than 0.2, go to your table, I get 0.5793. Okay, now from there, I want to do it again. Okay, that's if one male is randomly selected. But this time we're going to do a safety check and on the run of 100 helmets, and we need to see how the probability is affected by that change. So part B, again, probability is X is less than 6.3. So my z-score is 6.2 minus 6.0 over 1 divided by the square root of 100, which is 10. So 6.2 minus 6.0 over 1/10. And see what happens this time. So 0.2 on top divided by 1/10 on the bottom. I get a z-score of 2 this time. So looking that value up, I get 0.9772. Okay. And you can cross out part C. Okay. Same thing on number 7. Okay. Cross out part C on number 7 as well. Okay. So all I'm asking you to do is to perform the calculations. Now, one of the things that, because this is the last unit we're trying to wrap up before the end of the semester, one of the things I told the other class, the college algebra class, is as we introduce these new sections, you might want to go to that test. The test flows in the same order that the units do. So as they go from one topic into the next, you're going to see that they're going to make the changes just like we are in the homework. And you'll see maybe they won't necessarily spell out that it's a new unit, but they will say some of the vocabulary that we've been using unique to each section. So take a look at those questions. You might be able to answer some of those questions on the test while this information is fresh in your mind, and then go on to the next unit. Okay, so keep that in mind as you go through and do all these. So anytime you want to jump and go to the test and then come back and then move forward, it might be a good way to hit stuff while it's fresh. And you'll see also from that, you'll be able to identify what's really important out of these sections. And if there's something that's still causing issues, then you can email me and say, okay, this is what I need more help with. Okay, so make sure, communicate with me, guys. So that gives you a little bit, enough to, I think, where you can get some of these problems done. But if you're still having issues, okay, give me a holler.